So today begins our last introduction for the course. The first topic that we talked about was the topic of permutations and how those permutations begin to get us to think about braids. Right? So we used anagrams as a way of getting to that study, using anagrams to think about what a permutation is, and then using these funny braid-like anagram diagrams to show how we can think of an anagram as having some sort of a knot-like flavor to it. And then last week we introduced rational tangles, which was a way of taking the idea of braids, which are all twisted in one direction, and introducing a rotational element to it so that we could do some vertical twists and some horizontal twists, and we could mix and match them. And rational tangles gave rise to an interesting algebra structure, just like braids did. And so in today's class, the third of our three introductory experiences, we're going to finally meet the main player for the course, which are knots. And so we'll talk some today about what knots are, sort of how do we define a knot mathematically in a way that's satisfying enough for us to have, interesting structures we can do stuff with and also get to some algebra. And then the main topic that I want us to be thinking about today is the idea of what's called a knot invariant. An invariant is going to be some property that we can attach to knots that we would like to be able to use to tell two different knots apart from one another, and hopefully be able to tell when two same-looking knots are in fact the same knot. So knot invariants are going to be the things that we're going to try and chase down the most as we start studying knots, because they're going to be ways for us to capture as much of the interesting structure of how a knot is knotted together in as simple and we hope as algebraic an object as we can. So that we can do stuff with those values. And we know that the stuff that we're doing also corresponds to stuff that we would be doing with the corresponding knots. So for today, the type of knot invariant that we're going to study is a colorability invariant. That's why I had you practicing with the Zoom annotation coloring tools before class started. We're going to use the ways in which we can color a knot diagram as a way of getting at the idea of what a knot invariant is and how we can use coloration to tell one knot apart from another knot. So that's going to be the main goal for today. You can actually find digital virtual versions of the first few manipulatives of today's activities here in the textbook webpage. So if you scroll down to here, for example, here's a picture of a knot that actually has a three-dimensional way to turn around and look at it inside of your browser. All these are powered by GeoGebra, by the way. So if you use GeoGebra in your teaching, this is an application of GeoGebra just living right inside of these web pages. And as we get onto the coloration activities of the day, there are some coloration little GeoGebra applets to play with a little bit later on. If you have a physical version of the knots for these activities, it might actually be a detriment in some ways. Having these two-dimensional representations called diagrams for knots is kind of the more important way that we want to be thinking about knots for today, because it really gets at the key problem that we have when studying knots, which is a representational problem. If you hand me a two-dimensional diagram, how do I know what actual three-dimensional knot that diagram is representing? How many different diagrams can represent the same three-dimensional knot? It's going to be the first question that we start to wrestle with as we get into today.